Alright, Module 5b. In 5a we covered integer arithmetic. We are still working on computer arithmetic, but this part is on floating point. So this is from chapter 3 of computer organization and design, and it's still some of this slides from Ron Demara at UCF. Let me just provide some overview. If you don't know how we convert binary numbers that have bits on the right side of the binary point, that's how we do it. Obviously, you're familiar with this part, that we multiply the bit by, this is the left side of the binary point. Integer numbers are assumed to don't have any binary points, so it's like only the left side. This part we multiply the bit by 2 to the 0, and then 2 to the 1, and then all the way. On the right side of the binary point, we multiply the bit by 2 to the -1, and then to the -2, -3, -4, and so on. So if we have a number like this, which is 1101, this side we're familiar with the conversion. That's a straightforward process. It gives us 13. On the right side of the binary point, we multiply the first bit, which is 0, by 2 to the -1, which is 0.5. Then we multiply the next bit, which is 1 here, by 2 to the -2, which is 1/4, or 0.25. Multiply 0 by 2 to the -3, and multiply 1 by 2 to the -4, which is 1/16, which is equal to 0.065. So in this class, I try to usually work with four bits on the right side of the binary point. So if you remember those bits, which is 0.5, 0.25, 0.125, and 0.0625, you should be able to solve the question that I give you. For more than that, you can use the calculator. You don't have to do it. But that's the first review, and pretty much that's the only thing you need to know before getting to this module. So, what is floating point? We are already familiar with this concept of scientific notation. This is used for showing really big numbers or really small numbers. So in a lot of, when you're working with atoms, you have very small numbers. When you're working with, planets, you have really big numbers. So if you want to show these numbers, you have to have some kind of notation. That is what we call scientific notation. Floating point representation is pretty much the same thing. So in the decimal, we're very familiar with this case in decimal. We have a normalized number that has 1 bit on the left side of the decimal point, and some 1 digit on the left side of the decimal point, which is a normalized number. And then we have a bunch of numbers on the right side of the decimal point. And we have a base of 10 because we're in decimal, and an exponent. In this case, it's 23. Floating point is basically scientific notation in binary. You have the same concept of normalized numbers, a base of 2, an exponent number, and so on. So there are different ways of, by the way, before jumping there, I just want to mention the fixed point. But there is something between integer and floating point, and that is fixed point representation. Fixed point representation has a little bit more accuracy than integer, because you actually have a binary point, or you have a decimal point, but the number of digits, or the number of bits that we have on the right side and the left side of the binary point, or decimal point, is fixed. So you always have 3 bits on the left side and 4 bits on the right side, and so on. For that reason, you can use integer arithmetic for it. You just have to pay attention to where the binary point is. So theoretically, what you get with fixed point is a little bit more accuracy. Your range is going to be smaller than integer. If you have 8 bits, for example, you can cover 2 to the 8 minus 1. But if you just keep 4 bits of that for the binary point, then your accuracy, the numbers that you can cover are going to be small. You just have 3 points, 3 bits on the left side, for example, and then you can cover random numbers from -8 to 7, right? So the trade-off here between the integer and the fixed point is that you can show numbers more accurately, but the range of numbers that you can cover are small. okay, with the same number of bits, of course. If you have 32-bit integer and 32 fixed point, you can cover larger range of numbers with the integer. But the good thing about fixed point is that you can use the same kind of hardware that you have for integer for fixed point as well. You just have to add some pre-processing and post-processing, very small things, to take care of the binary point and decimal point. Floating point is an alternative to fixed point that we don't really know how many bits we have on the left side or the right side of the binary point. This point floats, okay? That's the whole idea of having a floating point. The binary point is floating, okay? That's what floating point is. So we can show scientific numbers or floating point numbers in different ways. You're familiar with that as well. So for example, if we have a number like this, 0.232 times 10 to the 4, we can shift it left and shift it right and change the exponent, and it still will be the same number, right? So for example, if I shift it left, then I decrease the exponent, and it's still the same number. If I shift it right, then I increase the exponent, and it's still the same number. Okay, so all of these representations, all of these numbers are the same numbers. We can show them in a different way. We have one case that we call it the normalized form, and the normalized form is the case that we only have one digit or one bit on the left side of the binary point or decimal point. But because we can show these numbers in different ways, it is always desired, when you come to hardware design, it's always desired to have some kind of standard. Because too much flexibility is going to cause challenges for hardware designers. Okay? So we always like to have standards, and based on those standards we can design a hardware that can cover all cases. Okay, the idea is, let's create a standard of representation, and our hardware just follows that standard, and then we can support all of the numbers within that standard. So this is a desired thing to do, and that's what IEEE did. So if you're not familiar with IEEE, you should get familiar with that. As computer scientists, computer engineers, electrical engineers, they support a lot of conferences, a lot of journals, and so on. They have several standards. So one of the most well-known standards that they have is IEEE 754, which is for floating point representation. It's universally adapted, people actually use it in hardware design, in all types of arithmetic, and that's why we're going to cover that in this class today. It has two representations, it has single precision and double precision. Single precision has 32 bits, double precision has 64 bits. So when you increase the number of bits, as always, the trade-off is you're going to get more accurate numbers, you're going to get larger, you can cover a larger range, but the computation is going to be more difficult, the memory is going to be used more, and so on. The memory footprint is going to be larger. Okay, so what is single precision? Let's start with that. What is single precision IEEE format floating point representation? So we have three fields in the single precision floating point. One bit is the sign field, then we have an exponent field, which has 8 bits, and then we have fraction, which is also known as mantissa. It's a small difference here, but we don't care about it, but fraction or mantissa, they have 23 bits, okay? And if you want to do the conversion, if you have a number in decimal, as x is going to be equal to -1 multiplied by sign, which means if the sign bit is 1, the number is negative. If the sign bit is 0, the value is positive. Then we have 1 plus fraction. This is called significant. So because in the floating point representation, in IEEE floating point representation, we only work with normalized numbers. So it means that there's always 1 bit on the left side of the binary point. Representation is binary, so we can't have numbers from 0 to 9. In decimal point, if you just have 1 digit that can be 6, 7, 2, 3, it's still normalized. in binary representation, if you just have one single 1 on the left side of the binary point, that's a normalized representation. And for that reason, fraction is not showing that 1 point something. Fraction is only showing the right side of the binary point. But as users, as designers, we know that this should be converted to 1 point fraction, and that 1 point fraction is considered as significant. Okay, that's what is called significant, 1 point fraction. So for that reason, this is why we add 1 plus fraction. Whatever is fraction, we add 1 to it, we get 1 point something, which gives us the normalized number. And then we have 2 to the exponent minus bias. So there is a bias here, and then we have an exponent. The reason that we have bias because we want to have both numbers less than 1 and numbers greater than 1. It's basically 2 to the negative something and 2 to the positive something. Okay, so with 8 bits, you can have numbers from 0 to 255. But if you have a bias point here, which in this case the bias in the single precision is 127, by doing the subtraction, you can show very small numbers, something like 2 to the negative 128, to all the way to larger numbers. Okay, so this bias of 127, how it is used. We can have numbers between 2 to the negative 128 and 2 to the 127. Sorry, 1 to the 20. Okay, single precision, bias of 127. Okay, now let's start with an example. The best way to learn how we can do the conversion, and that can be a question in your quiz too, is through examples. Okay, so let's say you have a convolution-based DSP filter that shows a floating point variable float x equal to 36.5625. Okay, that's a floating point representation of that number. And this needs to be interfaced to the sensor data bus designed by another team. And what you want to do is that what you want to see is what is the binary number in the memory, or what binary number is passed through this data bus. Okay, in English, it means that I have this number just converted to floating point. Okay. Convert 36.5625 to floating point. So I'll do the first one, we do it together step by step, and then we have another example that I give you some time to do it yourself. So first step is going to binary. We have a decimal number, we have to convert that to binary. 36 on the left side is equal to 100100, and then we have 0.5625, which is equal to 1001 on the right side. This is 0.5, and this is 0.0625. We add them, this is what you get. Okay, the first step is you get the decimal, convert it to binary. Okay. Now the next step is going to be normalizing it. So this number is not normalized because there are more than 1 bit on the left side of the binary point. And what it means is that I have to shift things left or right depending on what that number is. In this case, because we have more bits, we have to shift everything right. Okay? So when you shift everything right, every time that you shift 1 bit right, you add 1 to the exponent. When you shift left, you decrease 1 from the exponent, subtract 1 from the exponent. So I have to shift it right 5 times, 1, 2, 3, 4, 5. And if I shift it right 5 times, my exponent will be 2 to the 5, 2 to the 5th. Does that make sense? Now I have a normalized number. Okay? Alright, so what do I do with it? Next step. When I have a normalized number like this, I can use the relation that we showed earlier to find the S, M, which is mantissa, and exponent. Everything we want to do here is really finding these fields. So this part is really like encoding. We have 1-bit sign field, we have 8-bit exponent field, and we have 23 bits for mantissa. We want to see what numbers should sit on those fields. Okay. So now we know that this is the representation we have, and this is the number we got. This is the normalized number we got in the last slide. Okay, so from this number, we want to find s and an exponent. Okay, sign is positive, it's a positive number, so it means that s is going to be 0. Then we have the Mantiso part. I mentioned that we don't show this 1 point something, 1 point fraction, because we already know that in floating point representation we normalize everything, so the number that we have is already normalized. So we save 1 bit of memory, that's the idea. We save 1 bit of memory by not showing this number. Because we already know it's normalized. So we get the fraction, and we have the 1 here. So we do the opposite thing here. We have 1 point, whatever we have on the right side of the final point, that is going to be my Mantiso, that is going to be my fraction. Okay, so m is equal to this part. Now, to calculate the exponent, we have to keep in mind that this number n that we see here is equal to exponent minus 127. It's a single precision floating point. We have the bias of 127. So this is n that we see here is equal to exponent minus 127. n is 5 in this case. So exponent is equal to n plus 127. Simple math. We have 5 plus 127, it gives me 132, but I have to convert it to a binary number. Okay, so this is going to be my binary number here. We don't show these numbers like 2 to the something, this is a binary number, 1 point something that is normalized. We don't show these because we know it's the part of the standard. This way we save memory to show this number. We remove those extra information because we created a standard for us and we have this sort of information. This is the pre-known information. Okay? Now, it's not done yet. We have more steps. We have to put together everything as a binary number. So obviously similar to the decimal point, you can keep adding zeros on the right side of the decimal point and it doesn't change any number. 0.1 is equal to 0.10, is equal to 0.100, doesn't matter. So we have to keep adding zeros until we have the 23 bits that we are looking for in the Mantiso. So if you go back to the previous slide, we have this, but this is not 23 bits. Our field has 23 bits, so you keep adding zeros on the right side, not on the left side. If it was on the left side of the final point, you can keep adding zeros on the left side of the number and it wouldn't change anything. Here you do the same thing, you keep adding zeros on the right side of the fraction, doesn't change the number, and now our field is complete. So you have as many zeros as we need to get to 23 bits. You have 8 bits of exponent here, 1 bit of sign. Alright, so now the very last step is showing it in hexadecimal. You have a 32-bit number, you put them in groups of 4, and then you convert it to hexadecimal. Okay. So this is how we go from a floating point number in decimal to a hexadecimal floating point representation. Does that make sense? Any questions?
Does that mean that 0 is just approximated since the Mantiso always has an invisible 1?
Like these zeros are approximated?
No, like if you have the number 0 in floating point, would that just be like, it wouldn't quite be 0, it would just be a really small number,
No,
right?
we have exceptions for 0, so I get to that point.
Okay.
For infinity zeros, we have some cases that we reserve those cases just to show 0.
Okay.
Okay, that's a good point because with this representation, then that's the question. With this representation, we can't ever show 0. Like, how do you show 0? Even if the fraction is 0, it's 1.0 multiplied by something. So how do we show 0? We get to that point. Yeah. There's a slide that I have a table that shows those numbers. All right, so this is your turn. We have number negative 17.5. I mean, obviously I shared that slide with you guys, but I want you to do it now, so don't look at the slide as much as you can. So negative 17.5, this is single precision format, and we want to show it in hexadecimal. feel like you can do it, and if you're confident enough to come here and solve it, raise your hand, and you will get common sense. So you get 5 points to your quiz. So we have everything here. Use the marker. And just explain every step that you're taking. Okay, the first step is going to binary, right?
Yeah.
So conversion to binary, and that's a correct conversion. On the left side we have 17, on the right side we have a 1. Go ahead.
Alright. And then, so the sign is 1.
Or you know the sign is 1, it's a negative number. Correct.
And then the exponent, okay, so we got to normalize this.
Yes.
We move the final point 1, 2, 3, 4, 4 spaces to the left. So
we shift everything right 4
the
times.
exponent is 4 plus the bias of 127. Yeah, and then so 131, and then I'll convert that to binary later. And then we have this is the fraction.
Yeah.
So
we ignore the 1 on the left side of the binary point, and everything on the right side is the fraction. That's correct, yes.
okay, so then derive the whole thing in binary is the 1 for the sign, and then 131 in binary.
It's 128 plus 4 plus.
128 plus 3 plus
Oh, no, it's
or no,
actually-
plus 2 plus 1. Then 2, 1, that's 8 bits.
Yeah.
Alright. And
That's
then
sign.
that's
That's
the fraction. And then to get to 23.
zeros. We don't have to do that. That's correct.
Yeah.
So after that point, that's correct. Good job. Remind me. Send me an email.
Yeah.
I know your name, but I might forget. If I forget, let me know. Good job. So this is exactly what we need to do. First step is, I quickly go over it here one more time. First step is, we know the sign. Sign is 1. It's a negative number. Then we convert it to a binary representation. This is the binary value for it. Then we have to normalize it. When we normalize it, we get 1.00011 times 2 to the 4th. We have the exponent of n plus 127. N is equal to 4. So we get 131. We convert it to binary. We have the exponent right there. And the mantissa is whatever we have on the right side of the binary point. Then we put everything together as a binary number. We have 1 exponent, mantissa, and bunch of zeros until we get 32 bits. And then at the very last step, we have to convert this binary representation to hexadecimal representation. Does that make sense? All right, so now that we know how to go from a decimal point, floating point number to hexadecimal, let's practice doing the opposite thing. So we're designing a PCI Express bus interface, and we want to transmit a single precision floating point number for MRI imaging medical scanner. Okay, now we have an oscilloscope, and we did the measurements, and the number that we are seeing on the 4 PCM data bus is this hexadecimal number, 0x43410800. Okay, so now we want to know what this number is in floating points. In English, it's going from hexadecimal to decimal. Floating point. Okay. So obviously the first step is converting this to binary. We have a hexadecimal number, and we convert everything to binary. Then we have to identify what the fields are. We know the first bit on the left side is sign, the next 8 bits are showing the exponent, and everything after that point is mantissa. Okay, so this is S, which is sine. The next 7 bits is this number that we can see here, and that is exponent, and everything else is mantissa. Okay, so sine is equal to 0, it means that's a positive number. Exponent is 134, but we already know that there's a bias involved. Okay, now we have to get the n through e minus 127. We should take the bias out of this number. If we do e minus 127, we get 7, or in other words, e exponent is equal to n plus 127. This is 134. Subtract this, and we get n equals 7. And then we have mantissa, which is this number here. Whatever we have. Okay, so now that we have the mantissa and we have the exponent, we can create the normalized number through this. The normalized number is going to be this, 1 point mantissa times 2 to the 7, which is the n here. So this is the number that we have. But to go to the decimal number, we denormalize it. So similar to the floating point, going from decimal to floating point, the first thing that we do is normalization. Here, the last thing that we do is denormalizing it. Okay? So we have 7 bits 2 to the 7. It means that if we want to get rid of this 2 to the 7, we have to shift things to the left and decrease the exponent. We have to shift it left 7 times, or shift the binary point right 7 times to get rid of the exponent. If we do that, this is the number that we get, denormalization. If you shift everything left 7 times, you get this on the left side and this on the right side. And here you can use your calculator to calculate this number. Okay. The number you're getting is 193.03125.
There's just a typo on the left for 1/32. On the right it's correct, but on the left it doesn't have the first 0 after the final point. For
Right
over
here?
what? No, when you convert to decimal. At the
Oh, very
bottom.
end?
Yeah, the 1/32.
I don't see that. So there's 1, like here?
No, to
The
the
second parenthesis.
yeah. When was the fraction 1/32?
Very bottom.
Yeah,
Second
very
parenthesis.
Left 0.
I still don't see it.
On the left side of the equal sign. No. Yeah.
Up here?
No, to the right of that.
Okay.
The 1/32.
Oh, okay.
Yeah.
Oh, this is wrong? Yeah.
It's good on the.
Yeah, you're missing a 0.
Yeah.
Sorry. Oh, you guys are accurate. Okay. Yeah, that's right then. Thank you. Okay, so that's a number. The opposite thing. I can ask both of these things from you. I can give you a decimal number and ask for hexadecimal. I can give you the hexadecimal and ask it to go back to decimal. So that was the single precision floating point. We also have double precision floating point. Double precision is not really different. We just have 64 bits instead of 32 bits. And my exponent has 11 bits, sine still has 1 bit, and then we have 52 bits of fraction or mantissa. Okay. And because the exponent has 11 bits, the bias will be 1023 instead of 127. That's 2 to the 10 minus 1. Okay. So now, going back to Brandon's question. So we have this floating point representations, but how do we show numbers like 0, for example? So we do have some of the combinations of the exponents and mantissas reserved for these specific numbers. Okay, some of these errors you can actually see when you're running your code. Sometimes you see another number, and that's what is happening here. But let's just start with the first one. If you want to show number 0, when the exponent is 0 and the fraction is 0, in both cases, single precision and double precision, this is going to be number 0. Okay, when both fraction and exponent are 0. But that is going to have some consequences that we can see in the next row, like this row here. So it means that my exponent can be numbers from 1 to 254, because 0 is already reserved for showing the number 0. And if I have an exponent number between 1 to 254, or for the double precision 1 to 2046, this is actually a floating point number. This is what we just practiced now. But if you get both of them 0, then it's a 0. If your exponent is 0 and your fraction is not 0, it simply means that it is not normalized. Because if you normalize it, then you're going to have something in the exponent. Your exponent is going to become something. So it's just a denormalized number. If you have exponent 255 and the fraction is 0, this is infinity. But that is reserved to show it's kind of like an overflow and underflow. Okay? And we talk about overflow and underflow in a bit. And then if we have exponent 255 and the fraction, a non-zero fraction, or exponent 2047, or a non-zero fraction for double precision, this is not a number. Okay? It can happen in your code. Anything can happen. You can, by mistake, you can read an address and move it to a floating point register. That can happen a lot. You can try it in Mars. You can read an address and move it to a floating point or something. Something can happen. It can mess up the floating point number. When you're programming, actually, I think, how many of you guys actually saw this other number before in your C code? So sometimes this is the reason. That's why it happens. Okay. So you're moving. Your program is somehow moving an address to a floating point register. Something is happening there, and when it gets to that point, it says, okay, I'm reading a register that is supposed to be floating point, but this is not a floating point. It is just not a number. That's one of the reasons. Go ahead.
I think when I've been coding before, I've seen not a number when I accidentally divide it by 0.
That can happen too. Yeah. So when you divide it by 0, that can happen. So that's not the only reason. There are a lot of reasons that you can get another number, but potentially, if you make a mistake, if you jump to wrong places in your code, if you have an infinite loop or some type, that can happen. Okay, so this is the double precision floating point. So now let's talk about the range that we can cover with the floating point numbers. So because exponent 0 is reserved for value 0, so if exponent 0, we're showing the number 0, we talked about it in the table. The smallest exponent that we can have that is still a floating point number is 1. So what it means is that the actual exponent is going to be 1 minus 127 is equal to negative 126. Okay? And the smallest fraction that can have is when everything is 0. So your significant is going to be 1.0. You have a fraction of 0 and an exponent of 1. That is the smallest number that we can show. Floating point, single precision floating point representation. And that number is going to be positive or negative 1 times 2 to the negative 126, which is almost equal to 1.2 times 10 to the negative 38. So this is the smallest number that you can show with floating point representation, with single precision floating point. This is a pretty small number. With double precision, you can cover smaller numbers, even smaller numbers. Yeah. So what is this is the smallest one. What is the largest one? So we have exponents of all ones reserved for infinity. So if you have exponent 255, based on this table, it's already reserved to show the infinity number. So it means that the largest number that I can have in the single precision floating point is an exponent of 254, because 255 is reserved, and a fraction of all ones. Everything is 1, 23 ones. So this is really close to 2 when you input the significant here. If you do the conversion, you're adding 0.5 to 0.25 and 0.125. So if you add everything here, this number is not exactly 2, but it's really close to 2. Okay? So what it means is that you have 2, and your exponent is 254, so then you're going to have the actual exponent of 127. So the largest number that it can show is either positive or negative 2 times 2 to the 127, which decimal is almost positive negative 3.4 times 10 to the 38. So So this is the largest number that they can show. Overflow happens when your numbers are larger than this. When you have large numbers that are bigger than this number, that's an overflow. If you have numbers that are smaller than 1.2 times 10 to the negative 38, that's called underflow. So floating point numbers cannot show these huge numbers and these very small numbers. So that's the range that you can cover with a single precision floating point. With double precision floating point, you can cover way smaller numbers and significantly larger numbers. Okay? Any questions? Now, how do we do with this information about floating point? How do we do floating point arithmetic? Okay, so let's just start with addition and subtraction. At this point, we don't even care about binary or decimal. Okay, because we are familiar with doing this in decimal. So I just want to remind you how we do it in decimal, and then I'll let you know that it's exactly how we do it in binary as well. Okay. So what we do is we convert the operands to have the same exponent value. So if you have two numbers, if you want to add or subtract them, for example, if you have 2.1 times 10 to the 3, and if you want to add it with 4.3 times 10 to the 4, the first thing we do is we change the operands in a way that they have the same exponent. Okay. After having the same exponent, we can simply add or subtract the significance and keep the exponent as is. This is 2.1 times 10 to the 3. I shift it right once and add the exponent. I get 0.2 and 1 times 10 to the 4. These are the non-equivalent numbers. Okay. Now my exponents are equal, 10 to the 4, both of them. I can simply add the significance. This is the significant in decimal. In binary, significant always has a 1 on the left side of it. Okay. If it's normalized, and if it's not normalized, it has a 0. Okay. But then we add the significance and we keep the exponent. As simple as that, right? Subtraction and division are even easier because what you do is simply multiply or divide the significant part and add or subtract the exponents. So if I want to multiply, let's say 5.6 times 10 to the 12, and I multiply that with 6.7 times 10 to the 11, I multiply 5.6 and 6.7 and add these exponents. You multiply these two and add the exponents. This is simple math, exponent rules. And if you want to do the division, you divide the significance, 5.6 divided by 6.7, and then we subtract the exponents. 10.12 minus 10.12 minus 11, it gives me 1, right? These are simple exponent rules. But these simple exponent rules are also giving me some idea about what my hardware should look like. If I want to design a floating point adder, if I want to design a floating point multiplier, I have to take these steps, similar steps, to complete that, okay? So today, I think we have enough time for me to show you one floating point addition. Okay, and then next session we'll talk about floating point multiplication and continue from there. So we have this block diagram here. Again, this is one of those flow charts that you need to follow if I give you a question like this. And there are things, because usually we can't solve 32-bit digits here in the class, it's going to take forever. So we use smaller number of bits, but the idea is the same idea for 32 bits. Okay. So example I have here is that we want to add two numbers, 0.5 and negative 0.4375. We want to add these two numbers, and we are assuming that we have 4-bit precision. In single precision, we have 32 bits. Here we have just 4 bits. Including the bits on the left side and the right side of the binary point. So when I said 4-bit precision, I don't mean 4 bits on the right side of the binary point. I mean everything is 4 bits. We just have 4 bits. That's it. So the first thing you need to do is let's just convert them to binary and then start from there. So 0.5 is this in binary, and negative 0.4375 is this number in binary. Just keep in mind that when I ask you to do addition and multiplication, this is a different question from converting it to decimal or converting it to floating point. Okay, so when you convert it to floating point, it doesn't have to be iteratively format, floating point representation. It just goes to binary. Okay, so we're here at binary. Now, if I normalize this one, I get 1 point, and we have 3 zeros because we have 4-bit precision. 1.000 times 2 to the negative 1. And in this case, I shifted left twice to normalize it. So I get negative 1.11, then I add a 0 here, because I have 4-bit precision, times 2 to the negative 2. I shifted it left twice, so I decrease the exponent by 2. Okay, so now we have this. We can start, this is the first step. You just convert it to binary and normalize it. Okay, so now we can start the flowchart. The flowchart tells me compare the exponents of two numbers that I have here and shift the smaller number to the right until the exponent would match the larger exponent. Okay, so you compare the exponents, you get the smaller number, you shift it to the right until we get the same exponents. Okay, so let's do that. So this is the smaller number, 2 to the negative 2. Okay, so we keep this as is, we don't change that one. But we shift it right once, such that we get the same exponent. Every time you shift something right, you add the exponent, right? So you add negative 2 to, you add 1 to negative 2, you get negative 1. Now, they both have the same exponent. Okay, so at this point, we go to the next step, which is step 2, in which we add the significance. Okay, so you simply add the significance. We have 1.000 and negative 0.111. If you add these two, it's similar to subtracting 1 from 0.111, and this is the number that you will get. 0.001 times 2 to the negative 1. Exponent is not changing. Okay, so now I did this. I need to go to the next step. The next step is normalizing the sum. Okay, so this is the result. If I want to normalize it, I have to shift it left 3 times. Okay, and then decrease the exponent to get that number, right? So let's see. I shifted left 3 times. I have 1.000 and decrease the exponent 3 times. So I get 2 to the negative 4. Okay. So now I have to check if I'm getting an overflow or underflow. Okay, overflow and underflow, it has something to do with the exponent. The exponent I'm getting here is n plus 127, negative 4 plus 127, exponent is 1 through 123. So it's in the range of 1 to 254. If I do the sum, if I do the normalization at the end, my exponent is either 0 or 255, that shows an overflow and underflow, okay? So if there's no overflow happening here, we're good. We don't have to activate an exception. If there was an overflow and underflow, we activate an exception. And this guy here, this is responsible for giving you those messages in your program. So exception is just going to print, this is not a number, right? So this is what exception does in many cases. So we check for the overflow and underflow. We don't have any overflow and underflow. Okay, so now we go to the next step. The next step says round the significand to the appropriate number of bits. What it means here is that until this point, I can go ahead and don't care about the 4-bit limit that I had. So in this example, we don't see that because I didn't want to overcomplicate it. But you can go ahead assuming that you can have more than 4 bits. At this point, when we are shifting things right and left, you can go beyond 4 bits. Okay? So here you have to shift it left and right in a way that everything fits in 4 bits. This was already fine, so you don't have to really change anything. The sum is already fit, it already fits 4 bits, and you're good. if you have some extra bits here, like for example 1.0001, then you will get rid of those extra bits. But getting rid of those extra bits start a completely new conversation about rounding. So we don't have the rounding here, and I didn't talk about rounding because next session we're going to spend a lot of time on explaining how we round things. Okay? When you have extra bits, and you have, in this example, we could have had 5, 6, 7 bits here. Now, how you want to get rid of them, because you can't simply say, you can, the one way of them is just like truncate it, and just get rid of everything on the right side. But that's not the way it is actually working in floating point representation. Okay, we don't need to talk about it now because we talk about it next session. But you don't need rounding here, so you're good. And you just check if it's still normalized. And in this case, it is still normalized, so you're good. And then you have the result. The result is right there, 1.000, I have turned to the -4, and which is equal to 0.0625, which is the right answer. You actually do the subtraction here, do this addition, that's the number that you're going to get. Okay. Now, these are the steps that we need to take to do an addition or subtraction. Let's take a look at this block diagram. So this is, if I ask you to design a floating point adder, you should have followed this block diagram. So when I took computer architecture as a graduate student, I was a master's student at the time, I was in an ECE department, and we had to design these stuff. So that's why I decided to do it last year, and I learned the hard way that I shouldn't do it here. So we were supposed to design these things. So our projects in the computer architecture course was design the hardware for floating point, design the hardware for floating point arithmetic, design the entire processor. So at the end of the course, I had a MIPS processor design on chip. So we could actually run the processor on FPGA, we could test it. Hopefully at some point, actually the advanced digital design course here does the very similar thing with RISC-V processor, which is a little bit more advanced. So that's one of the reasons that I also stopped doing it, because that course already exists. And if you're a computer engineer, if you're into designing FPGAs and chips and stuff, you can take that course. But so our project 2, I think, was designing the floating point. We had to do like 8 projects at the time. So this was the block diagram that they provided to us, and they said, okay, design the floating point. So let's take a quick look at it, because I want you to see the difference between the floating point arithmetic, floating point addition, and an integer addition in terms of the hardware. So in the very first step that we compare the exponents, we do compare the exponents here, but then we have the small ALU that adds or subtracts the exponents. The exponent is looked at as an 8-bit integer number, and you do some kind of comparison right there. Then we get the exponent difference. We have an entire control signal here, which helps with shifting things left and right. So if you want to shift the significant left or right, depending on the difference in the exponent. So we compare the exponent, and then we have a shift register. We start shifting things left and right to get the same significant. Then we have a big ALU, because in real case we have 32 bits, right? So when you were adding the significant here, this was a very small number. When you want to add the significance there, this is actually a big number. It has 24 bits, okay? So we're adding two 24-bit numbers, but the significant is really like a fixed point. So when I talked about the fixed point, we already know that there's always going to be 1 bit on the left side and 23 bits on the right side. So you can use an integer ALU to add or subtract the significance, okay? Then you have, based on that, you start doing the normalization, you decrease or increase the exponent. And again, you shift things right and left. And then you have the entire rounding hardware. So I don't want to talk about the rounding hardware, but that's something that we cover in the next session. But then we have the entire rounding hardware, just to see what that last bit, the least significant bit in the mantissa should be. Okay, so look at everything that you see here. An integer adder It's just this guy. That's it. So instead of having 24 bits, this is a 24-bit adder. That's a 32-bit adder. But we already have another 8-bit adder here too, right? So if you just want to visualize what it takes to do a floating point add compared to what it takes to do an integer add, just look at this guy here and get rid of everything else. We have an integer add, then add everything, bring everything to the picture. You have a floating point add. Okay, so let's go back to neural networks. So last week we had this vector multiplication, vector matrix multiplication, and so on. So you guys are dealing with integer arithmetic now. A lot of neural networks, when they came out at the beginning, they didn't care about, and this is exactly how programmers think. They don't care about the hardware. Like at the beginning, you just want your code to work, right? So they were like, sure, why don't we use floating points? Cool, let's do it. So in a network, in a lot of practical models that we have these days, like recommendation systems, 85% of the alphabet revenue is coming from recommendation systems. Okay, so those guys have a lot of matrix vector multiplications. So it's simple, fully connected networks, matrix multiplication. We are talking about billions of parameters. We're talking about billions of floating point arithmetic operations. We're not talking about 2, 3, 4, 5, 10, 12, right? Billions of them. Like those metrics that we have right now, that you're working with nits per milliwatt. They're working with tops per watt. So tops is 10 to the 12 tera operations per second, per watt per second. So when the first machine learning models, they were not even considering these limitations, okay? NVIDIA jumped there. It's okay, let me design a GPU that does floating point really good. That's the whole idea. Like the whole entire idea of GPU. Before that, we have a lot of GPUs that they were designing. We get there. I don't want to go way ahead of myself, but we talk about GPUs in the very last module of this class. But GPUs were designed to work with pixels and do some simple arithmetic to render graphics, right? But what are the other arithmetics? Those are floating points too. So NVIDIA as a GPU designer, and then we had AMD too, right? AMD was designing GPUs. Xbox is still using AMD. I used to, before getting this job here, I was offered the job at the R&D of GPU design for AMD, and they were designing GPU for Xbox. So AMD didn't use this opportunity as well as they could. They didn't really believe in machine learning models that much, AI, but NVIDIA did. So what they did was they saw that we have to do billions of floating point arithmetic operations, and they designed GPUs that are really good at implementing floating point arithmetic. Just floating, and not everything. In neural networks, we have floating point add, floating point multiplication, and that's it. So there is an entire industry built around floating point arithmetic, right? It's very complicated to do. And it's also these days with machine learning and everything, we use them a lot. Then in 2017, I'm giving you a little bit of history of machine learning and hardware. In 2017-16, Google, not a hardware company, Google, came up with something called tensor processing units, TPUs. We had GPUs, then we had TPUs. So the idea behind TPU was, I use a systolic array. I don't want to talk about the systolic array here, but their idea was, okay, let me use 8-bit integer arithmetic. They extended it later to floating points, small floating point numbers, and so on. But at the time, they showed orders of magnitude improvement in its speed when they went from floating point to integer arithmetic, 8-bit arithmetic. So my goal in this project, when we design the projects for you, we start with integer. Then we go to floating point. You do the operations with floating point. Then I want you to test this vector-vector multiplication. We go to the extreme. We try to have like 1,000 by 1,000 vectors or something, 256 by 256, so you can actually see the limitations on the memory. And then you can test the word if you have 32-bit, or if you have a byte, or if you have a floating point representation. And then you just look at the memory and see what happens in the memory. So we're going to cover the memory block later. It's the module after the processor. So next module we're going to talk about the processor. After that we talk about memory. Then you play with the memory policies, different policies that we have. You see how your cache works. And then you see how big of a deal it is to know this number of representations in today's world, right? I emphasize one more time, the tensor processing unit, TPU, we actually have the Google's chips in the lab. Brendan's actually working with some of them. And then we have like Intel's VPU that they have like 32-bit floating point representation, and we compare them and do benchmarking and stuff. But Google is not a hardware company, right? So computer scientists, if you think computer architecture is not for us, we're just here to take this course as a core course, we hate it. So Google designed a processor that they're hoping can compete with NVIDIA and Intel and AMD and these guys in terms of how fast they can process a machine learning model, right? So it's a very naive way of thinking if you just jump to your code and do the programming and you think people are gonna be happy by your code being functional. Okay, so your choice is either being at the edge of the research and startups and whatever, or just working in a company that cares about functionality, that your code is functional. If you're working in a company that they care about your code being functional and not optimized, that's a sign to know that you're not working on a cutting edge thing. Okay, so that is what matters. When you simply go from floating point to integer, if as a person, as a computer scientist, you do see the value of, okay, this is the part that I can go to an integer and don't lose accuracy that much, and save that much time, that much energy, that much speed, then you are different from others. So hopefully we get to that point. But that was just me showing you that what happens when you simply use the float in your code instead of an integer. Every time that you say float 1.0 and you don't really need that everything after the decimal point, you're just killing the processor for no reason. So don't create a loop and use floats and say, okay, it doesn't matter. But it does matter. Okay? So hopefully we're going to see it in the class, but I think we're done for today. We talk about it next session, and then after that we're probably going to have a quiz. Okay.